Okay, so hello everybody, and this week we're very happy to have Evan Mcdonough. I may not be pronouncing that correctly, but correct me if I'm not.
It's perfect.
Okay, from the University of Chicago, who will be talking to us about slow gravitinos. So, Evan.
Okay, thank you for inviting me. Thanks everyone for coming. Today I'm going to be talking about some work that's been really fun. We've had these two papers out about this topic, and we have a couple more papers in the works, in particular with an eye towards dark matter and things like that. And the general theme here is about production of gravitinos and more generally spin 3/2 particles. And so I should mention today is based on these two talks that I wrote with Rocky and Andrew. And this has been a ton of fun, and it relates to such a huge extent to the foundation that was built at Stanford, particularly in this broad research program, which is to understand our universe using quantum gravity and to understand quantum gravity from observations of our universe. And as a baby step towards full quantum gravity, it's convenient to, as a baby step, to look at supergravity. And what does supergravity get you ostensibly is the gravitino. So a large part of the focus today is studying the gravitino, the quantum field theory of the gravitino in curved space, and the phenomenon that's one of the most fascinating aspects of quantum field theory in curved space, which is the production of particles when the vacuum state of your theory is changing. And then I'm going to talk about the possible connection of this to the Swampland program in the string theory community. But first, I'd like to just start by laying out some of the broad context, which is here I'm going to be tying together sort of three distinct threads. And I guess I'll mention that to me, one of the most exciting things is getting to tie together different directions into one cohesive narrative. So the cornerstone of the analysis, and I'm going to present numerics and analytics, is this phenomenon of particle production from looking at quantum field theory in curved space. This really goes back, I believe the first mention of this is Schrodinger in 1939. And I think the most famous example, of course, is Hawking radiation. In the cosmology community, this notion of you have a quantum field theory, we define particles with respect to some vacuum state. When that vacuum state changes non-adiabatically, you can go from having a state with no particles to then your late time observer looking at the out state will see particles. And this is the basic physics that happens at reheating. In the context of dark matter physics, this is really championed by Rocky, and his first iteration was referred to as Wimp-Zilla's, and he's been carrying forward that research program of this gravitational production of dark matter ever since then. And in the context of inflation, it's really neat. You can have this particle reduction happening itself during inflation. It can lead to tons of cool observables. In fact, it leads to its own inflation scenario that was developed at Stanford by these authors. And more recently, in some work with folks at Chicago, Keisuke, who's another postdoc, and with Wayne Hu, we studied how primordial black holes can actually form from the particles produced in one of these non-adiabatic events. So what I'm going to be connecting this phenomenon of particle production with is some of the big breakthroughs in supergravity that have happened in the last 5 or so years, which really all came out of Stanford. And the hallmark success is this theory of pure de Sitter supergravity. And out of this theory framework comes hundreds of cosmology papers studying the cosmology and how inflation can come out of this, including this is my small contribution to this field. Now, the third corner I want to connect with is in the string theory community, in particular, sort of the East Coast string community, is this swampland program in string theory. And the reason I put a question mark here is that it's not obviously the case that the swampland program has anything to say about supergravity constructions of cosmology. And the few attempts that were made to say what these swampland conjectures, what they have to do with de Sitter space and string theory or the supergravity realizations, they ended up, not holding any water at all. And this was shown in this series of papers that by myself and Marco and Renato and Andre. So the common theme here being that both Marco and I were visiting Stanford in 2014, sort of being flies on the wall while this sort of stuff was happening. And it later grew into these papers. So let me say a few words about what is this swampland program. And it's the general idea that we have some theory of quantum gravity, and it's fairly well established that there is not just one solution, there's not just one vacuum. In string theory, so as what was envisaged in the 1980s, as we would have some theory of everything, we just needed to find that one solution. But in the early 2000s, we realized that there's actually a landscape. We now fast forward 20 years, and the question has sort of morphed into, we know that there is some huge class of models. There's an infinite set of Lagrangians that you could just write down. And which of those Lagrangians actually come out at a low energy limit of quantum gravity? So which of these models actually lie within that landscape? And in the context of this hierarchy of energy scales going to different effective field theories, we know in the deep UV, at least in the context of string theory, we have this two-dimensional world sheet theory. As I flow down to lower energies below the string scale, the theory is well approximated by 10D supergravity. And below the KK scale, where I'm compacted by my extra dimensions, I get out some 4D supergravity theory. Below the SUSY breaking scale, I just get out some particle physics model of cosmology. And what I want to ask is, focusing on at this stage here, thinking about these 4D supergravity models, how does this interface with the swamp? And this is what I'm going to come to near the end of the question, is just, does there even exist? Can we establish the existence of a swamp for supergravity cosmology models? And the playground for this, of course, is cosmology. And over the last 10, 20 years, it's been pretty firmly established that cosmology is a great playground for these ideas and for stress testing theories of high energy physics. And the basic reason for that is, in the context of inflationary cosmology, it's quantum vacuum fluctuations during this period of inflation that make up everything around us, which is to say, the large scale structure of the universe is seeded by these quantum fluctuations during inflation. So there's some background rustling. Okay, fine. So again, this is this notion that we have quantum vacuum fluctuations. Every particle that's coupled to gravity will be popping in and out of the vacuum during inflation. So what that means is, when the adiabatic curvature perturbation pops out of the vacuum, and these perturbations are exponentially stretched during inflation, eventually they reach the horizon, and we see this imprinted on the CMB. But every particle that is coupled to gravity, which is all particles, are also popping out of the vacuum. You can have scattering events and loop corrections occurring during inflation. And this changes the correlation functions of this adiabatic curvature perturbation. And so how we can observe this is in the statistical properties of the cosmic microwave background, which are in correspondence with the correlators of your field fluctuations during inflation. This has been popularized lately under the banner of the cosmological collider physics program, where it's one of the big emphases is looking at higher spin fields. So, some spin 35 boson, how would we know that that exists just by looking at the cosmic microwave background? And I've worked on that a bit myself, worked with Jim Gates and collaborators at Brown, studying how a higher spin fermion is imprinted in the cosmic microwave background and a supersymmetric theory of higher spins. We have some paper on dark matter in this context as well. So it's pretty firmly established that cosmology is a fantastic place to do particle physics. So to drive home this point of particles coming from inflation, I think it's really the case that inflation is a particle factory. And here let's just look at one case study, which is an example of a heavy particle. We know that the basis for this whole formalism is that on small scales deep inside the horizon, we quantize our fields as if we were in Minkowski space. You just say we impose Bunch-Davies initial conditions on the quantum fluctuations. And by solving the directly equations of motion, you can find the solution on large scales approaches as a Hankel function and some exponential suppression coming from the mass. Now, if I map this onto the vacuum state of the quantum field theory in whatever phase follows inflation, what you go from having is just this positive frequency mode to actually having both a positive and a negative frequency mode. And it's the coefficient of this negative frequency mode, which is the Bogoliubov coefficient, which is your smoking gun for the presence of particles with respect to this post-inflation vacuum state of the quantum field theory. And the secret ingredient, which leads to the existence of these particles, is that the vacuum state during inflation is changing non-adiabatically. So for example, here, this is the dispersion relation of this field, of this heavy field during inflation. And we diagnose this notion of adiabaticity by looking at how the dispersion relation is changing with time. So omega k dot over omega k squared. This is a dimensionless quantity that parametrizes how the vacuum is changing. So at early times, it's 0, the vacuum is nearly constant for all k, and it approaches 0 at late times. And there's some intermediary time where the vacuum is changing, and the change in the vacuum state is order 1. And this occurs, usually we refer to horizon crossing, Hubble horizon crossing, being k is equal to AH. This happens when k is equal to MAH. So this is the sense in which inflation gives you particles. And this is the simplest context, the simplest setup. In fact, the most dramatic effect actually happens at the end of inflation in the oscillating phase. And indeed, this is the focus of most of the work on the phenomenon of gravitational production of dark matter. Just one second. Right, now, one of the fascinating aspects and what makes this both studying high energy physics in the context of inflation both necessary and exciting is the well-known UV sensitivity of inflation. And as a case study is large field inflation. Now, large field inflation itself is, I think, like a wonderful setup and is my favorite context for inflation. In particular, if you just think of m squared phi squared, you have some parabola potential. It doesn't matter how high up you start on the potential. And it also doesn't matter what initial velocity you have. The inflaton can be kicking up, it can be shooting down. Hubble friction will slow the field down and you'll eventually enter a slow roll phase. So it's extremely natural for inflation to come out of a large field context. But in this modern framework of thinking about effective field theory, and this is borne out when you think about large inflation, supergravity, and the string theory, we know the inflaton potential itself, it receives corrections suppressed by your UV cutoff. And so let's say you have some series of irrelevant operators and the UV cutoff is the Planck scale. Well, if the inflaton is 10 m Planck, then these would be small corrections. Suppressed corrections are not suppressed at all. And this is an example of what's known as the eta problem. And so these corrections generically ruin the flatness of the potential, preventing you from getting 60 U-folds of inflation. Now, the way out of an eta problem, generally speaking, is to introduce a shift symmetry for your inflaton field. And historically, the first example to do this was natural inflation. You say you have a cosine potential, and if the decay constant in your cosine potential for this axion is Planckian, then it essentially becomes like m squared phi squared inflation. Now, the problem with this, which has been studied in a huge amount of detail in recent years with the weak gravity conjecture, is that this cosine potential is itself only the leading term in a harmonic expansion. And I should say that this argument actually goes back to Tom Banks, pointing out that this is a harmonic expansion. And when you make the axion and the k constant super Planckian, this expansion is no longer well approximated at all by the leading term. And there's been some nice recent work by John Stout, which talks about how do you make sense of this expansion when all terms start to become important. I think that's interesting. Now, the other approach, which comes out of Stanford, is the setup of axiom monodromy. And in that case, you don't require a small you don't require a large decay constant. So if you still have Planckian field excursions, then in that case, the field is moving, say it could be hundreds or thousands of decay constants. So the basic premise here is that you have some form field and extra dimensions, which the shift symmetry is coming from the gauge symmetry in the higher dimensions. So you have, in your internal space, charges conserved, you have a Gauss law constraint in this internal space. And that tells you, even if the fluxes of the charges decreasing locally, for example, the amount of flux locally on a brane, the charges are really just being shuffled around in your internal space. And this leads to sort of back reaction effects. And one sort of fantastic result in this context is that the back reaction of monodromy inflation can lead to a modification of the potential, which itself can be observable. So this not only can studying the UV completion and tell you whether or not your theory is self-consistent, but it can also sometimes lead to observable effects. And I'll briefly mention actually one model which seems to be somewhat free of UV sensitivity is alpha attractors, and I think that that's itself pretty neat. So faced with the UV sensitivity and the question of how do we make sense of this, the starting point, the baby step, is to look at supergravity. So let's get started, and just the simplest possible setup, which is n equals 1 supergravity. In the textbook, and the textbook in this case being Freeman and Van Proyen, is absolutely fantastic. So the setup here is we go from gravity, where the force carry is the graviton, having a graviton and a gravitino. So in this case, the gravitino is spin 3/2 particle, and local supersymmetry is the gauge transformation of the gravitino. You have the spin 3/2 gauge invariance. Your scalar fields, such as your inflaton, get promoted to be complex scalar components of some set of chiral superfields, so superfield living in our 4D spacetime, and also a set of fermionic coordinates that describe superspace. And the action is specified by two functions, k and w. K is known as the Kähler potential. It defines your field space. It's a real function. W is defined as the superpotential, or referred to as a superpotential, and it's a holomorphic function of these complex scalars. And these K defines the field space, and K and W together determine the potential. And in a background that breaks supersymmetry, which is any cosmological background, in analogy with the Higgs mechanism, you have the Einstein super-Higgs mechanism, where instead of a Goldstone boson, you have a Goldstino of SUSY breaking. And the gravitino eats the Goldstino to become massive. And the gravitino mass is determined by the Kähler potential and the superpotential. So as I mentioned at the outset, one of the huge breakthroughs in supergravity came in recent years with this advent of de Sitter supergravity. And the name of the game here is to introduce a field S, which itself is nilpotent. It satisfies a constraint equation that squares to 0. And when you're in superspace, you have these x and theta coordinates. This constraint is itself actually 3 separate equations, solving each order in theta, the fermionic space coordinate. And if you're in a SUSY breaking background such that this auxiliary field F is non-zero, there's a non-trivial solution where the scalar component is related to the fermion component. Now, if I plug this solution back into the Lagrangian, what I end up with is a theory with the cosmological constant. And we're giving the vacuum state, the ground state of this theory is de Sitter space. And when I go to unitary gauge, so that's the gravitino eats the Goldstino, the theory here describes only a graviton and a massive gravitino, and they're propagating in a de Sitter space. And alongside, what's nice about this is when you're dealing with this type of field satisfying this constraint equation, is that the most general superpotential you can write down is linear in that field. Any higher order terms would vanish by this nilpotency constraint. And I think what really makes this a huge success for theoretical physics generally, not just in the small corner of supergravity, is that de Sitter supergravity is itself the effective field theory of an anti-brane, which is to say, the anti-3 brane, which is the secret sauce, well, not so secret, in the KKLT setup for de Sitter space in string theory. And perhaps the technical details aren't super important for today, but let me mention that it was realized in this paper, and I did some follow-up work with my supervisor at McGill, Keshav. And so Keshav was on sabbatical here the year prior, is that the fermions that live on this brane effectively get Higgs, and they get Higgs by the background form fields, these fluxes, by those fields getting a Bev. And when you do dimensional reduction to get down just the 4D field content, what you find is that you have 4 fermions, 3 of them get a mass just from these background fields, and 1 of them remains massless. And this massless field is itself the Goldstino of SUSY breaking. And when I repackage the field content, what you get out really is de Sitter supergravity. And I mentioned that there's some nice extensions you can do of this, such as extending this beyond just quadratic order in the fermions to this is the action of describing an antibrane is really an alpha prime expansion. And you can extend this to, in fact, it's pretty remarkable to include all orders in alpha prime. And then I'll also mention that if you include, I mean, the significance, I didn't say it in words, but here we're fixing the position moduli that describe the motion of this brane. If you allow this antibrane to be mobile, so it's moving around your internal space, the scalar fields that describe the position of the antibrane themselves satisfy their own constraint equation. This is called an orthogonal constraint. And this leads to what's known as minimal supergravity inflation. And this is, when worked out in detail, was sort of discovered and worked out in detail by Tim Rice and Renato when Tim was a postdoc at Stanford. Now, the appeal of de Sitter supergravity to cosmologists writ large is that it's really easy to build cosmology in de Sitter supergravity. As I mentioned, the most general superpotential you can write down is just a linear term plus a constant. So now if I take sort of the general paradigm for building supergravity inflation models is to write down some Kähler potential that has some symmetry in some field components. So here, this may look ad hoc, but this is, I have some field T, and this function here has a scale symmetry in T. So I take the magnitude of T and I rescale it. This whole thing is invariant. So an idea that was in these 2 papers here was that if I have some small correction to the Kähler potential, which mixes this field T and the nilpotent field S, that itself can lead to a cosmology. In particular, you could get straightforward out of this from W, you get the cosmological constant. And from this Kähler mixing, you get out inflation. So here, inflation for the field phi, which is the magnitude of T, which itself is otherwise a shift symmetry, has a shift symmetry in the Kähler potential. And this model setup, I mean, it's really like a one-liner to write down the model, and then you can show all the fields are stabilized. It's actually a working model of cosmology. It has some neat features, such as one, the Gravitino mass is a constant, which is sort of a weird feature in supergravity, you might think naively, because the Gravitino mass principle depends on K and W. But in this type of setup, the Gravitino mass is in fact a constant. It has this other feature that SUSY breaking, we can think of there being a direction to SUSY breaking, where we have a field space manifold, and certain fields break SUSY to certain extents, and this allows us to define like a vector in field space, which is the direction of SUSY breaking. And in this context, SUSY breaking is orthogonal to the cosmological evolution, which is to say it's the field S, which is breaking supersymmetry, but the inflaton is the field T. And it has this other nice feature that the inflatino, which is the fermionic partner to the inflaton, has a mass which itself is tunable, which is to say at the end of inflation, the mass of the inflatino is parametrically heavy, depends wherever I want to put the minimum of the inflaton potential. And I'll emphasize these features 1 and 2, that the Gravitino mass is a constant and SUSY breaking is orthogonal. It was really coming from the fact that after I impose this nilpotency constraint, the field space as defined by K has an unbroken global U1 symmetry, which is this shift symmetry for the magnitude of T. And this is something that we're still thinking about now, and possible connections of this.
Evan, can I ask a question? Sorry.
Yeah.
Just saying, I mean, more general superpotentials are possible though, right? It also have T dependence. So
right.
isn't that property then spoilt once you include the most general possible superpotential?
That's right. Right.
Oh, okay, good. Right. So this
So
is a special feature of just this one you've written down.
Right. Right.
Okay, thank you.
So I give this as just a sort of exceptionally simple, definitely not the most general at all, but it's a working model, and it doesn't take a lot of creativity to come up with it.
Oh no, fine, absolutely. Yeah. I'm happy with toy models to get some intuition.
So I'll zoom in on the Gravitino, and I'm working in this context where the impulsino is heavy, and so I can really just be studying the spin 3/2 particle with some mass, and that mass is in principle time dependent. And after much sort of a detailed calculation, and sort of the mass of spin 1 can be decomposed into spin 1 and then spin 0. Here you have your mass of spin 3/2 gets decomposed into helicity plus or minus 3/2 states and helicity plus or minus 1/2 states, and they form their own. The helicity 3/2 and helicity 1/2 have their decoupled Dirac equations. And what's interesting is the helicity 1/2 state. In fact, you can see that the coefficient of the momentum piece is not identically 1, but in fact is built out of these parameters. And if I square the Dirac equation to make a Klein-Gordon equation, what I really find is a dispersion relation for this field, which is instead of your usual p squared plus m squared, the speed of what we call the sound speed, this is the spatial momentum, cs squared, is in principle not equal to 1. It's not the speed of light. And in fact, this is the sound speed here, and it depends on the mass of the field, the evolution of the background cosmology, here R is the Ricci scalar, H is the Hubble parameter, and on the time dependence of the Gravitino mass. And you can work out expressions for how the sound speed looks in various supergravity setups. So here's one, and there's an infinite number of ways you could express it. But here's one simple form, which I think provides some geometric interpretation for what is the sound speed of the Gravitino. And here we're looking at, you can define a vector, which is the field space evolution along some direction in field space. And the SUSY breaking, I can write down the F term, the SUSY breaking of each field. So I can find a vector in field space that is the SUSY breaking. And the sound speed depends on the angle between these two vectors. And it's when if these two vectors are parallel, then I get that the cos theta is 1, and this whole correction goes away. And when these two vectors are orthogonal, cos theta goes to 0, that I get the maximal deviation from 1. And if the SUSY breaking is equal, if the SUSY breaking vector, the magnitude is equal to this time derivative vector, then in that case, actually CS can pass to 0, which I'm going to talk about in a minute. But this general phenomenon of the sound speed itself is not in general equal to 1, but you can prove it's bounded between 0 and 1, is known as the slow Gravitino. And that name goes back to this paper from 2014. And a lot of the machinery, all of the machinery actually, for this goes back to the early 2000s work by Renat and Andre and collaborators. And you can work out the sound speed, how it looks in different classes of supergravity models. For nilpotent models, it's not changed at all. You can go to these orthogonal nilpotent models and it's changed slightly. This itself is not super important for today. The feature I'd like to emphasize is that the sound speed can vanish. And so let's consider the simple case of a gravitino that has a constant mass in an FRW space. And in particular, this is a sound speed in some FRW space with a general equation of state. Let's consider a radiation-dominated universe. So W is equal to 1/3. And let's consider the possibility that at the beginning of the onset of your radiation-dominated universe, the Hubble parameter is larger than the mass of the Gravitino. So you have radiation-dominated universe with this huge value of H, and then the radiation starts redshifting and H is decreasing as you go about your cosmological evolution. So at early times, H dominates and CS squared is equal to 1/9. So that's what I'm done here. Now I know at late times when H goes to 0, so all this radiation has redshifted away, then C squared just goes to 1. But at some finite intermediary time, the sound speed will always touch 0. And this is the minimal assumptions to do this is this constant mass gravitino in a radiation dominated universe.
Evan, can I ask you a question, since this is
Yeah.
a crucial thing? So there's a question about whether this is a physical effect or it's just a breakdown of the approximations you've used at various stages. Because, of course, there are other fermion fields around,
Right.
and there are various fields that are time evolving.
Right.
So the question is, I mean, after all, people said things like, if you have like an inflection point, an inflationary potential, you would get this, hugely enhanced, 1 over epsilon parameter, inflationary epsilon parameter, density perturbation spectrum, delta rho and rho. And of course, that's not true, because now when epsilon is going to 0, there are subleading terms in expansion for delta rho and rho, which actually make things finite and sensible. So the question is whether there are this feature. I could certainly believe you could get very close to 0, depending on parameters. But the question is whether you literally go to 0, and whether that's just a feature of truncating the expansion, expansion for CFS. I mean,
so one feature I'll point out is that if you look at the full supergravity action, including all the 4 fermion terms, like the torsion term, for example, which is a 4 gravitino term, there's no k to the 4 term. There's no subdominant k to the 4 term, which would take over when CS goes to 0. So that's point one.
It's more like the fact that in realistic models. I mean, actually all models, there are time evolving scalar fields, and there are also other fermions. I mean, you have to worry, and you have to do the full mixing matrix, right? Between all the fermions is the crucial issue.
Right. So here, that's what I'm saying. I'm working in the simplest possible setup where there is an inflaton which is evolving, and SUSY raking is orthogonal. And I'm taking the inflatino to be heavy. So in that context, if the inflatino is heavy and it's above whatever the UV cutoff or when some new stuff should be appearing, inflatino is heavy, then this is the simplest possible thing I can write.
Fair enough. So let me rephrase the thing.
Yeah.
So my question is whether this 0 is really not 0, but 1 over the inflatino mass.
That's an interesting question. I can't confirm or deny that, but if that's quantitatively the answer, but it would be neat if that did end up being the answer.
So that's my sharp question. Okay.
Yeah.
Great. Okay. Right. Thank you.
Thanks. Right. So this vanishing of the sound speed not only can it happen in a radiation dominated universe, but it can also happen at the end of inflation. And in particular, as you make the mass of the gravitino lighter and lighter than the Hubble parameter at the end of inflation, it can vanish many, 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 many times. And again, this happens under this, you're working in the simplest possible model you can construct, not the most generic. And if the mass is less than the Hubble parameter. I'll emphasize, even in these simple models, what is the simple feature of these models that's making this happen? In large part, it's the fact that the field space itself has this global U1 symmetry, which makes the gravitino mass identically constant. There's this shift symmetry in K and W that's necessary to get n3 halves be a constant, because I mentioned there's so many ways you could express the sound speed. This is one way in terms of the pressure and energy density of the background and the time dependence of the mass. So the time dependence of the mass makes a positive definite contribution. So any non-zero time dependence will lift these zeros. So it's in order to have CS vanishing, you need to have this identical shift symmetry in K after you impose the no potency constraint. Now we think that we have a really good handle on quantum fluctuations during and after inflation. So what happens to the gravitino fluctuations that are produced during inflation if after the end of inflation, they go through this period where the sound speed is vanishing? And one answer right off the bat, analytically, is that the vacuum state of the quantum field theory is changing non-adiabatically. And again, working in this simple limit where I have this heavy inflatino, and I'm considering a constant mass. So if returning to this adiabatic condition that we have omega k dot over omega k squared, in a conventional setup, this always goes to 0 when k goes to infinity, because omega k squared itself should go to infinity when k goes to infinity. So this combination should go to 0. But if you compute this for this general dispersion relation and you just evaluate it at moments when the sound speed vanishes, what you find is that it's actually equal to h over m. And it's particularly in the case when m over h is less than 1 that the sound speed can vanish in the first place. So this tells you that this quantity is necessarily more than one in the situations where the Gravitino sound speed can vanish. And what's sort of curious about this is that, or perhaps obvious, when CS vanishes, K drops out of the dispersion relation. So this violation of adiabaticity then is K independent. So what we did was to go ahead and try to study this system numerically to try and see how is this analytic intuition borne out. And here's just some of the technical details, but maybe what I'll emphasize is that you have your Dirac equations for the 3/2 and the 1/2 so this is the modes. And from this, you solve these Dirac equations and you compute the Bogoliubov coefficients, which is the asymptotic limit of the negative frequency modes. And then from the Bogoliubov coefficients, you compute the spectrum of particles. So as a prelude to the numerics that we've done, let's take a look at what was done circa the late 90s, early 2000s, which was to look at just a single chiral superfield, so a single field setup. And a feature which makes this simple is that, as I mentioned, there's a geometric interpretation of where is this reduced sound speed coming from in terms of angles on field space. And if your field space is one-dimensional, then all vectors are parallel, and this CS is always identically 1. And you can derive that in a number of ways, but CS is equal to identically 1 if you have a single chiral superfield. So this is the numerical results from this paper from 1999 by Anthony Riotto and Igor Kachev and Giudice. We're looking, this is the helicity 1/2 mode for different sets of parameters. And the general feature you observe is that this is the spectrum versus K. It rises and rises and rises, then it turns over. And as you get to higher K, that can start probing the fact that the background cosmology itself is oscillating, then you start getting these fast oscillations. And you see this sort of independent of parameters. This is always a general trend, rise, rapid fast oscillations. So now let's go to this case where we can have a vanishing sound speed. And on the left, we're looking at the time dependence of this process for individual K modes in the context where the sound speed is vanishing shortly after the end of inflation. And on the right, we're looking at the spectrum, so the whole set of K modes. Let's start on the left here. So this is the Bogoliubov coefficient, K cubed beta squared. And what you can see is for these different K modes, there's this synchronized rise of all the beta Ks. It happens is driven by this vanishing sound speed. And when you do this for a huge number of Ks, you compute the Bogoliubov coefficients, you can check the spectrum, what you find is on the right, where instead of the production turning over at some finite K, instead it rises and rises and rises, it starts undergoing fast oscillations, and you can compute it off of this graph, and it continues rising and rising and continuing to undergo these fast oscillations. And if the only minimal change you have to do to sort of shut this off is just raise the mass up to the Hubble scale. So in this case, there's no zero touchings of the sound speed. It goes down to 0.4, and the production is tamed. So now you find that it goes up and then turns over and starts oscillating. The helicity 1/2 is still enhanced from these oscillations and its reduced sound speed, which makes it a good dark matter factory, and that's what we're working on now. But the feature that it goes and goes and goes is actually is tamed. Right. So what are we to make of this? That in a set of simple models of m is less than Hubble parameter, you can produce particles, it seems, of arbitrarily high momentum. And this is what we called in our first paper on this catastrophic production of slow gravitinos. And I think it's reasonable to say what happens when you have such a phenomenon is that the effective field theory itself is breaking down. In sort of the classic sense of the qualitative picture of what is Wilsonian effective field theory is that there's some length scale, and you've integrated out all physics happening on scales smaller than that. If you produce a particle with momentum K at the cutoff, you start probing the physics at length scales below that. And concretely, just within the effective field theory, you can consider that there's some tower of operators, which is suppressed by powers of the cutoff. And here the cutoff is of the supergravity model. And these come with they come with the Gravitino mass, because this M3 halves is the order parameter of the spin 3 halves gauge invariance, and the order parameter for the breaking, rather, of the spin 3 halves gauge invariance. And if I produce a particle with K at the cutoff, then this whole tower of operators becomes important. So you can see sort of from a qualitative picture, or in terms of including corrections from whatever is UV completing 4D supergravity, that the effective field theory will break down if you start producing these arbitrarily high K modes. And I'll emphasize that this is qualitatively different from the conventional Gravitino problem. So the usual Gravitino problem is more of an inconvenience for anthropic considerations, which is to say the universe becomes dominated by Gravitinos, or the Gravitinos overclose the universe. That's really a shame for us, because we can never come to be. The theory at all times is well posed. Like the quantum field theory that describes these Gravitinos, there's no, it never breaks down at any point. But here it's really a breakdown of the theory.
So just to come back to the thing that John was asking earlier. So we get arbitrarily high momentum if CS goes exactly to 0, right?
Yeah.
So what you were saying before seemed to make it sound like it's not clear if CS does go exactly to 0. There might be contributions to it that are suppressed by some kind of scale separation, in which case, would that mean that we didn't have this picture then?
Right. So those numerics and full analysis has not been done. So here, but there you can identify the simple class of models where CS would identically touch 0.
For a symmetry reason, is that definitely
Partly
true? Or is it just like, okay, I'm not quite clear. So we're saying that within this model, which still has a UV completion, so like even with the full UV completion, CS identically goes to 0, or is it just like?
Oh, no, I'm saying it within the UV completion, it definitely does not go to 0. But the fact that you need the UV completion is itself interesting, I think. So that's what I'm about to say is that, so I think that there's no way in the UV complete theory, or in the whatever is UV completing this theory, that the time speed vanishes. I think that so what I would argue is that this is a relic of the supergravity model as written down, is not including all the information.
And so just
sorry, I have to push back with that. I don't think you really know that. I think the supergravity model as written down could contain all the information, because, as I said, you've made this extra assumption of taking really the Inflatino mass to infinity. I mean, it's not really infinity, right?
Yeah.
And so you have to do that analysis, and it could be you still get an enhanced, which of course is still very interesting for things like dark matter production, but it doesn't literally go to infinity once you include that effect.
I mean, with the KK scale is 10 to the minus 3 M Planck, and then Inflatino is 10 to the minus 2 M Planck, then you have this whole tower of KK modes that you start probing before you start exciting Inflatino.
Yes, but of course you can always have new physics happen at a lower scale than your true cutoff when other things. That's always possible. The question is whether there's whether it's possible to write down a supergravity theory, not a string theory. That's the difference. I mean, a supergravity theory that has a consistent description of Gravitino production. That's the issue.
Oh, definitely there exists a supergravity theory which has a consistent description. I think I'm asking the opposite question of, does there exist a supergravity theory that is inconsistent when you consider Gravitino production?
And I
like it's definitely the case that it's trivial to write down a supergravity theory which would be consistent. So it's only if you make very special assumptions that you can find a supergravity which is inconsistent.
Fair enough, but I don't think you haven't really convinced me that you've done the analysis, you've dotted every I, crossed every T, as far as that was exactly the question I asked earlier.
Okay. So let me give like the punchline and a couple comments to it, and then we can come back to it. So the claim I was going to make is that supergravity models where it does identically touch 0, those effective field theories are not themselves coming from quantum gravity. In a model that you would actually derive from quantum gravity, you would have these additional terms, or the Kähler potential would have corrections to it, which generates time-dependent gravitino mass, this sort of thing. So let me say concisely that this phenomenon never happens in the landscape. And just the same with that, the sound speed, and there's a more precise definition of this, which is you have in general, you have kinetic mixing, you have a sound speed matrix. So the sound speed here being the determinant of a matrix of all the fields that are kinetically coupled below the cutoff. So the sound speed can never vanish, and we call it the Scraptino Swampland Conjecture. And they're similar to saying that there's no global symmetries, meaning no exact global symmetries. It's just a non-vanishing statement. So in principle, this statement is happy with CS being arbitrarily small but non-zero. So in that sense, it's near trivial to satisfy. But in fact, it does have some interesting consequences.
Excuse me, Evan, haven't you actually shown us that this conjecture follows from the no global symmetry result? Because your models where CS goes to zero all had this U1 global symmetry. Yeah,
so that's something we've been thinking about. I'm not aware of the discussion of no global symmetries where it would be on, like, in this sort of supergravity contexting of the Kähler potential and the field space manifold. But so yeah, what we've been wondering about is how actually like cut and dry is that connection. But maybe, or you're the expert.
It's a very general result. It doesn't, it doesn't matter whether you have supergravity or don't have supergravity. So I would have conjectured that you'd always have some higher dimension operator where you broke the symmetry. You might be able to introduce some gauge discrete symmetries that prevented operators up to some dimension, or something like that. But
so for example, in a stringy setup, you always have GS and alpha prime corrections in the Kähler potential, which would break these symmetries.
Right. Exactly.
So I think that this is the reason we tried to frame it in the most conservative possible way. I think that it's definitely the case that this is positive in setups that you actually derive from string theory or any quantum gravity. So we sort of just hinted at the ways out of this. Let me just reiterate that for the simple model I wrote down before, the sound speed could vanish. So it's not the most general model, but it's at the face of it, a perfectly reasonable model, and many people have written many papers on models sort of similar to this, and the sound speed can vanish. But it's sort of simple to bring models back to the landscape. And here's one type of setup showing how once I turn on a time dependence to the gravitino mass, how I lift the zeros of the sound speed. So here's the type of setup where I'm introducing this orthogonal field, and I have some parameter alpha, which parameterizes the time dependence of the gravitino mass. So let's just focus on this plot on the left. So when alpha is equal to 0, this is the sound speed, it touches 0 every oscillation. And as I turn on alpha and I lift the zeros and I make alpha order 1, then the oscillations themselves aren't even visible anymore. So it's really, if I break this global U1 symmetry, which generates the time dependence of the gravitino mass, I lift these zeros. Right. And if you accept as a null hypothesis some of the assumptions I've made here, and you don't, so that's what's fun about this. Let's just say you have this constant mass gravitino, and we're assuming a conventional thermal history where inflation or radiation dominated universe. This gives you a couple options, which is if a gravitino is observed, we know this connection, we have this connection then between M, the gravitino mass, and the Hubble parameter at the end of inflation. We know that if a gravitino is observed by us humans, the gravitino mass it's not going to be too much bigger than a TeV scale. It could be hiding in the LHC data right now. We know the B modes and the CMB are connected to the energy scale of inflation, so H. And it's only if H is extremely high in our anthropic units that B modes will be observable. So if in the context of this simple null hypothesis, if you do observe a gravitino, if it's hiding there in present LHC data, then you'll never see B modes because the tensor scale ratio will be too small for any conceivable future experiment to measure. And the converse of that, if you do observe the primordial beat modes, this would suggest that the Gravitino.
Sorry, Evan, I'm completely confused by
Right.
that statement you just made, because the amount of supersymmetry breaking during inflation and the amount of supersymmetry breaking now can be completely disconnected from each other.
Yeah, they can be, and so this would tell you that. So yeah, I would say that.
Then I just don't understand the wording of one. Maybe I'm being stupid about reading it. So
so this assumes you have a constant mass Gravitino.
Oh, you mean over the entire history of the universe?
Yeah.
Oh, yes. Okay, well that's a big assumption. Okay, fair enough.
Yeah.
Yes. All right.
So then, if you observe both of these, you've sort of discovered that how SUSY being broken is changing over the course of the cosmological evolution.
Okay, fair enough.
So depending on how you feel about SUSY, I think that would be an obvious thing, or that would be like a huge discovery. That's somewhat a matter of taste. Both of these things independently, B modes, Gravitinos would be discoveries, and in putting these things together, you can learn something about SUSY breaking cosmologically. Right, so I'm almost just on time. So let me give a quick summary, and then I'll give some directions for future work. One, I tried to emphasize that I think cosmology is a great playground for stress testing theories and studying high energy physics. And in particular, what we've been looking at here is massive spin 3/2 fields, which have this curious feature that there's a modified dispersion relation for the longitudinal mode, which is helicity 1/2 component. And the curious feature is that they have a sound speed, and that sound speed can vanish. And it's epsilon away from trivial to write down a SUSY model, a Sugar model where that happens. And if you make certain simple assumptions, when the sound speed vanishes, you can be producing particles arbitrarily high K essentially for free. And the Gravitino Swampland Conjecture is just the statement that this can never happen in the landscape. And in terms of where to go next, I think it would be neat to connect to, since then there's been 2 other Gravitino conjectures, one by my collaborator, Marco, and his collaborators, and as well by these authors, the Gravitino mass conjecture and the Gravitino distance conjecture, which both pertain to, as you take the limit that the Gravitino mass goes to 0, there should be some tower of light states which emerge, which is a close cousin to the statement that the effective field theory is breaking down. Of course, it'd be neat to extend this also to extended SUSY like n=2, n=4. And our initial goal and what we're trying to do now is studying Gravitino dark matter and the connection, how the sound speed can enhance Gravitino dark matter production. And then finally, going from spin 3/2 to arbitrary spin. So in the spirit of the cosmological collider physics program, and the paper I wrote with Jim Gates and Stefan Alexander and Stefan's student Leah and Jim's postdoc Konstantinos on studying higher spin fermions and inflation and their imprint on the CMB. Right, and with that, I'll say thanks.
Okay, well, thanks very much for a nice talk. Let me stop the recording.